Hi, I'm Graham Marshall. I'm the site manager here at the Chilbolton Observatory. A day here is very varied. We have such a vast array of instruments and scientific experiments going on that every day is different. So one day I can be tracking satellites, the next day I can be 30 meters up in the air fixing a light bulb on the side of the antenna. Behind me here is the optical tracking system. We use it for tracking satellites and objects at LEO, MEO and GEO and beyond GEO. We've had the instrument now for about 8 years, but this year we've installed the new dome, which allows us complete autonomous and remote operations. It has 2 telescopes, and from that it gives us options to mount multiple different cameras, a standard optical camera, or we can choose between medium wave or short wave infrared. We upload the information into the NSPOC, the National Space Operations Centre, which feeds an overall model of where spacecraft are at any one time. We've got a vast programme of upgrade works to install on our antennas. We've got new equipment and new buildings coming into site very soon, and my proudest achievement will be to see that through to the end.
My name is Emma Rumi. I am an RF engineer working at the observatory since 2015. The best thing about working at the observatory is the opportunity to be involved in a variety of activities such as satellite tracking, developing instrument, developing a new mission, developing new ideas, and within that you have the opportunity to work with partners, with universities, researchers, and come up with the new ideas to develop future technology. Well, this is a ground-based demonstrator for a radar, and this is to prove a concept of a new space mission called BARODAR, and that stands for Barometric Differential Absorption Radar. This is how it starts. We develop a ground-based instrument, then we move into an airborne instrument, and this is to prove the concept before going towards space with expensive project. This project will measure the pressure on the surface of the Earth globally, which doesn't exist at the moment, because at the moment it's only measured by weather stations put on land. And as you know, the 70% of the Earth is water, which is difficult to put any weather station. So there are very few, and we only measuring 30% of the Earth at the moment. But with BARODAR instrument, we will have a global measurements which help predicting the weather, forecasting the hurricanes, tracking their tail, and the main point of impact.
Hello, my name is Josh Key and I work as a maintenance technician. A typical day for me, generally I'll start out with some routine things. I might go around checking instruments, making sure they're all working. So for example, the various rain gauges we have here. I might also have a look up in the dish, check everything's all operational up there. Then after I've completed the routine stuff, I might go fix up something if it is showing signs of any breakage issues that's going wrong with it. So this here is a drop counting rain gauge. So they were originally developed here about 25 years old, but they still have some advantages over more modern equivalents, such as their accuracy. So on the top, this green piece here, the little funnel, catches water over a slightly wider area to give you a better result. That goes down through a little tube into a brass block, which has small little kind of tank reservoir thing, you might want to call it, and some little capillary tubes that basically funnel all that water into individual drops. That goes through in here through a optical sensor, which detects from the rate of the drops falling through the rain rate. One thing I'm very proud of working here is just getting to work on lots of unique and interesting pieces of equipment that you might not be able to find in various other places. I mean, for example, the radar dish here, I think, still holds the record for being the world's largest fully steerable meteorology dish, which is quite an impressive thing to work on.
My name is Keith and I am an instrument engineer here at Chilbolton Observatory. First thing in the morning, I normally look at the instrument status and look at the data products. And after that, the sort of routine goes out of the window and you need to attend to any faults or any data products that look a little bit suspicious. They need to be investigated. In addition to the drop counting rain gauges, we have many other types of rain gauge, and one example is here on my right, which is a weighing rain gauge, which essentially is a bucket on a scale. Rain can affect the propagation of radio signals, particularly at the higher frequencies. So we need to be able to compare the attenuation of a radio signal with the rain rates as they are occurring. There's now a lot of interest in higher frequencies for satellite applications, and we are currently looking at the rain effect on those higher frequencies.
I'm Richard Reeves. I'm Principal RF Engineer here. I do a lot of work designing, building, maintaining and upgrading the radars that we operate on site. Today I'm talking about the radars on the big dish behind me, which we use for satellite tracking and for weather observations. It is the world's largest fully steerable S-band weather radar. It's also one of 2 radars in the UK that are routinely used for satellite tracking. It's the only one that is civilian operated. And it gives us the opportunity to experiment with different ways of operation. There are a large number of satellites in orbit. Not all of them are operational. It is very common for predictions of where those satellites are to overlap. So you've got a potential conjunction or collision in space. So we get tasked to look at the targets of interest to the UK government, so that's UK registered satellites, and check to see what their latest positional information is, to see whether there really is a risk or whether it's just old positional information that's causing the alert. What I'm most proud of about the observatory is our ability to adapt what we do to meet the requirements of the various research groups or the users of the data, and the growing international collaborations that we have to use that data on a much larger scale.
My name's Alistair Mallet. I'm the mechanical instrument technician at Chilbolton Observatory. I enjoy working at the observatory because it's something a bit different. It's situated in a really nice part of Hampshire as well, so it's always nice to come into work with the countryside around. But personally, my career path was mainly heritage steam locomotives and railways. So it's nice to be able to use my skills in heavy engineering in a place that does scientific research. So at the moment we are situated in the machine cabin of the 25 metre dish. We're actually on top or inside of the 420 tonnes of metal superstructure that sits on the main azimuth bearing. So here at the moment is one of the 4 motors or motor gearbox sets that we have that go onto the main azimuth ring. At the top we have a motor. It's only about 150 newtons in force, and then it goes into a speed reducing gearbox. So it doesn't have to be very strong as such because it's transferring speed into torque. Interesting fact is once it's all gone down through the gear train, we have actually got a hand wheel that we can put onto the top of it and replace one of the motors, release the other brakes, and actually move the dish around by hand. I like working here because I'm able to put on a pair of overalls and still get dirty. As much as I like clean engineering, this is definitely the hands-on dirty side of it. This is original 1960s equipment, having been with the dish when it was commissioned. And then on top we have a new motor arrangement with a system drive upgrade to better aid for accuracy. But what's quite good is we can incorporate the more modern motors and technology onto the much older mechanics.
Hi, I'm Tim Thornton, I'm a mechanical engineer and I've been working on the Spectre ground station. So Spectre is a quantum demonstrator satellite. It's a CubeSat, it's about the size of a couple of shoeboxes, and this is the ground station. So this is what will do the communication with the satellite. It receives a quantum signal using this big telescope here that we've modified, and it will have these laser beacons around the side of it. And the idea behind these is to form a big bright light that the satellite can look at and transmit its data down to the ground station. It's custom built. We've modified an astronomical telescope for this purpose. The idea is that there could be lots of these around the country and around the world if this test all goes well. I'm normally based in Rowell, so when I come down here it's for testing, for integration and calibration. So we'll normally come down in the evening, set everything up, so then when it's dark we can run our tests, which could look like pointing at stars and seeing how stable the system is, or we could be tracking some space junk. It really depends what we are trying to do, but mainly testing and integration.
Hi, I'm Eve Pryor. I am an industrial placement student doing radio frequency engineering. A typical day, that's really hard to answer just because I do lots of different roles. I kind of do a lot of different tasks. I'm trying out a lot of different things at the moment. So something I've been doing a lot of is soldering and testing printed circuit boards for the big antenna upgrades that are going on here at Chilbolton. And recently, just this week, I have been learning how to use the satellite tracking that we have going on as well. My favourite thing is getting to try out lots of different things, especially as an industrial placement student. It's really helpful just to see what different kind of things I could potentially go on to do. So LOFA stands for Low Frequency Array, and it is a big radio telescope. So this station is part of one out of 52 stations across Europe. So it combines thousands of dipole antennas, so it's really helpful to astronomers and it's given lots more data to them. Currently we're standing with all of the data processing, so this is where all the data is received from the antennas that we have. This will be sent to the Netherlands for all the data acquisition and post-processing. So what's special about LOFA is it works at really low frequencies, so from about 10 megahertz to 240 megahertz, and it's a great pathfinder for the square kilometre array. We're looking to go and look at more space weather applications, so researching the structure of solar wind and solar flares and how they interact with Earth. So that's quite a big feature, and there are upgrades that are coming, so that's LOFA 2.0. So I'm quite proud about the outreach stuff that we do here and my future role in it. So we had some work experience students back in the summer just when I started, and that was really fun to get to learn alongside them and also just kind of teach them a few things and see what they were interested in, and I'm quite excited for the future outreach projects.